Welcome to topic 1, the first topic proper of this course in statistics. Previously, we had a little introduction to the subject, and as part of that introduction, I discussed how we'll be progressing through this subject from looking at experimental design, in that how do we derive data, how do we sample a population to derive data which allows us to tell a story about that population. Then we look at how do we summarize the data and describe the data that we've found. That's descriptive statistics. And then we move into inferential statistics, which is how do we analyze the data? How do we see how good that data is in describing the picture that we're looking at? And how can we compare multiple sets of data to see which one is greater or lesser than the other, for example? We'll begin this topic by looking at key terminology to describe data sets and to describe experiments, because you'll be encountering this terminology frequently within this subject and within your reading. And there's some very important distinctions we need to make early on. From there, after we do this terminological discussion, I don't think I've ever used that word before, but there it is, terminological discussion, we'll move into the central tenets of statistics: the mean, also known as the average, and the standard deviation. And the standard deviation is essentially looking at how spread our data is around a particular average. And we start there because most statistics, really, certainly at the applied level that we look at it, and you'd need for 95% of your working life, is based around deriving these mean and standard deviations, and then analysing how good they are at describing the experimental system that you're looking at. So that's what we start there, and it also demystifies a lot or many of the items of angst that there can be in statistics. This first picture here sums up stats, I believe. It's an art installation where the letters are contributing to "you can't see the forest for the trees" are all laid over each other, which really describes statistics, because we often get lost in a massive data and we can't actually see the picture which the data is trying to show. And statistics is all about piecing out trends and patterns and pictures within the data. Let's begin our discussion on key terminology in statistics with a case study. And here's an example I've taken from the Australian Bureau of Statistics, which release nationwide figures on the state of the population every 3 or 4 years, including the health of the nation. They also do the national census, of course, which examines national income and ethnicity and where people are living. But they also have one in particular on the health of the nation. Here I've grabbed a graph looking at the change in average height between 1995 and 2011 of males and females in Australia. And again, this is just an example we're using to begin our discussion of terminology, but it's worth having a look at the graph in its own right. The difference in average height of males and females in the population, as well as how the average height of adults has increased over that period of time, but not teenagers and people in their early 20s. So as adults get older, they're now staying taller than they did even 16 years ago, both males and females. You can look at the entire study, all the data from the studies that they have done, looking at the health of the nation, following that link available there. So I asked on that previous on the previous slide I mentioned that as part of this overall health study, the Australian Bureau of Statistics look at the change in weight and height of the nation over time. We saw the data, or a graph showing the change in height of the population from 1995 to 2011. And the question is, how would we achieve this data? How would we gauge the average height of the nation? Well, there's two ways that we could do it. The first would be to take the height and the weight of every person in Australia. So that's currently 22.68 million people. So we'd find every single person in the nation, we'd get their height and we'd get their weight. We'd put it into a spreadsheet, maybe on Microsoft Excel, and we'd get the average and find out what that height and weight is. And as we saw from the previous graph, the average height of a 24-year-old male is about 177.5 centimetres. So that's one way of doing it. Now, that's an extremely comprehensive way of doing it, but it might actually not even be possible to actually find all 22.68 million people or convince them to come in to get measured, their height and their weight. They may be incapable, they may be sick at the time, they may be overseas, and it'll be extremely expensive. If it took you a minute to do the height and weight of every person in Australia, it would take you to 22.68 million minutes to take those heights and weights. So that's an extremely expensive and not an overly realistic method of doing it. The other way we could do it is measure a subset of all the Australians in this nation and just measure the height and weight of this subset or sample of the nation and use that to infer what the average height of the whole nation is. And this is what the Australian Bureau of Statistics did. In fact, if you follow that link, you'll see the exact methodology they used. But in summary, what they did, which was still a huge task, was they measured the height and weight of 1 in every 1,000 Australians. And they found these Australians from all around the country so that it was representative of the entire population. This sampling method, rather than this comprehensive method of measuring everybody, getting a subset, is a lot cheaper and a lot more practical than the comprehensive method. And also, if it's done right, it's nearly just as accurate. And really, this method that we call sampling, in inverted commas, is what statistics is all about. Very, very rarely can we measure every single individual in a population. Instead, we have to sample a population and get a subset. And then we use statistics to work out how good is that subset in gauging the overall picture of the population. Here is just a pictorial representation of what I was just saying. Imagine the population is this larger oval there containing every single possible individual, and our sample is just a smaller circle within that larger sample, within that larger population, just a subset of the overall population. And our objective of this sampling is to make sure that the data we get from this sample is as representative as possible of the overall population. So here we come to a list of these key terms and what they equate to in our example here of the Australian Bureau of Statistics health study. A population, the population in this case is every Australian. So the population is every possible unit that could be measured in the study. Individuals are the Australians that were measured to derive the average weight and height. So the population is every possible individual. A sample are the actual individuals that were measured. So they're the subset of individuals from the entire population. A variable is what is being measured. In this case, the variables were height and weight. If they are measuring hair colour, then the variable would be hair colour. So in a sampling operation, variables are measured from individuals drawn from a population. The data are the actual values of the variables measured. In this case, in this study, the actual values of the height and weight that were measured to derive those averages. In the experimental design phase of a study, you concentrate on working out where your individuals are that you're going to sample. Which individuals am I going to sample to get a representation of the population? Once you've done this experimental design, obviously your attention will then move to the variables that you're going to be measuring in these individuals. In the next topic, or in 2 topics time, we'll be looking at how we work out which individuals we're going to sample. But from here and into the next topic, we'll be looking at what type of variables there are, which we'd measure in individuals, how they're broken up into different categories, and how we can simply describe some of the data which comes out from the measurement of these variables. And there's 4 main types of variable that we'll encounter. They're first broadly broken up into numerical and categorical. Numerical can also be referred to as quantitative and categorical as qualitative, and we'll be looking at what each of these are in the next slide. Numerical in turn can be broken up into discrete and continuous numerical variables, and categorical can be broken into nominal and ranked variables. So let's have a look at what each of those are. So we have categorical variables, which are the qualitative variables, and we have numerical variables, also known as quantitative variables. Categorical variables and data derived from categorical variables occur when individuals are placed into groups based on particular traits, and these are generally traits that we assign ourselves, sort of overlaying on their biological status. So for example, blood group is a classic categorical variable. Which blood group are you? There's a discrete number of them. So there's, say 5 different blood groups. I may be wrong there. Hair colour, people are generally just broken up into blonde, brunette and black and grey. Nationalities, we divide into historic country distinctions of ethnicity often. So categorical data are when individuals are placed generally into discrete groups. Fish species is a classic one for that. Numerical data are when individuals are numerical data is derived from studies where individuals are physically measured. So there's a trait which is measured in the individuals. So it might be body length, it might be height, it might be weight, nitrogen level, pH of water. Here is a classic spreadsheet which shows both categorical and numerical data. First of all, in row 1, we have the actual variable which is being measured, specimen ID, which is really a code, stem length, so these are flowers or plants, number of flower petals and the flower colour. The categorical data here are those found under the variables of specimen ID and flower colour. So flower colour, we're pigeonholing particular flowers into particular colours. And numerical data, we're actually counting the number of flower petals, and we're using a ruler or calipers to measure the length of the stem of these plants. So it's quite clear which ones here are categorical and which ones are numerical. Don't fall into the trap that all numerical variables are always numbers and categorical variables are always words. You can see that specimen ID is actually their given numbers, but that is a categorical variable. So we've seen how categorical and numerical variables are defined. Now let's look at the subcategories within these two variable sets. Categorical nominal, categorical ordinal, numerical continuous, numerical discrete. So we can see here the distinctions are quite simple, and I should point out I'm using the term ordinal here, whereas previously I used the term ranked, but ordinal and ranked are the same, and in fact ordinal data is defined by the fact that it's ranked. But let's look at each one in order. So categorical nominal data, or variables that are categorical nominal, are those which are named. So we as humans apply a arbitrary name to them, which may be for historic reasons. Species is a classic nominal variable. We pigeonhole particular organisms into this manufactured classification, which is the species. Ethnicity is another classic one there. We're not measuring it based on particular enzyme levels. We're doing it on predefined names that we give particular groups of human beings or other organisms. So that's categorical nominal data. They're named. Categorical ordinal data is where we rank things. And the classic ranked variables are those when we have to do surveys. So when you're asked to disagree, if you're asked a question, it might be, how good is Alistair Reid? Or is Alistair Reid the best lecturer in the world? You're asked to tick disagree, neither agree nor disagree, or agree. Obviously it'll tick agree. But that's classic ranked data. And there's particular ways that we'll learn how you can analyse this ranked data, because it's a very, very common variable that you'll encounter. And so there'll be lots of data which you'll be encountering based on this measured variable. So that's the categorical classes, named and ranked. Fairly simple. Now let's look at the numerical variables, the ones that we actually measure. So we get data based on physical measurements of characteristics. The first is continuous data, where we actually take readings. A classic example of that is height of a plant. So here's the example, is height of wheat plants in a field. Earlier we looked at the height and weight of humans. That's a classic continuous data. It can go from 0.1 centimetre up to 2 metres and every millimetre in between. But they're measured. The other type is discrete, and that's actual counted data. So variables where we count things. How many grape varieties are in the vineyard? Okay, so just pause the video here and have a look at this question, where we're asking which of the following variables listed from this medical study are categorical, and then to throw a curveball, I ask which are quantitative. And remember, quantitative ones are numerical. So the question is, which of these variables are categorical and which ones are quantitative? And don't forget to go into the subcategories of each as well. And on the next slide we'll discuss the answers. Alright, so let's have a look and compare the answers I've given here to what you've derived. And please let me know if you think I'm wrong. First of all, we have gender, male or female. This one here I've listed as categorical nominal, so it's named data. Again, we're not looking at estrogen levels versus testosterone levels, a measured variable. We're actually just looking at the categories that we give to the two different sexes, male and female. Age is the next one, and this is numerical measured. So it's number of days alive. Here it's actually asking for years. State of origin, should be state or territory of origin, correction. And this is another example of categorical nominal. We're pigeonholing something, giving something a name based on where it's from. Smoker, yes or no? Again, this is a classic categorical nominal when naming it depending on categories that we give particular classes of organisms, in this case via their behaviour. Blood pressure is the next one, numerical measured. It's on a sliding scale. It's actually something we measure. We're not counting something, we're measuring something. Level of calcium in the blood, again, it's a measurement. It's the milligrams per millimetre. We're not counting. If we were counting the number of individuals with calcium which is greater than 50 milligrams per millimetre, that would be numerical counted. If we were ranking humans from highest level to lowest level of calcium in the blood, that would be categorical ordinal or categorical ranked. Okay, so let's look at how we deal with numerical data which is derived from measuring numerical variables. And numerical variables are those that can be measured. Of course, we'll be looking at how to analyze or describe categorical data down the track, but let's concentrate on numerical data for now, because it's generally numerical variables which provide us with larger data sets which we then break up. And often we actually use the categorical variables to structure our numerical variables. So for example, we may we may net a whole lot of fish. We may divide up that catch into different species and then measure the length of each species that was found. So really what we have there is a whole lot of numerical data which happens to be divided up into categories from categorical variables. So for the next little while we'll concentrate on this numerical data. And this may be data to do with grape bunch weights, fish lengths, the speed of horses, they're listed there, wheat carbohydrate content, anything along those lines. And after this sampling is undertaken, and remember the sampling component is when we determine which individuals of a population we're going to measure, we generally have a large list of numbers, and these are really meaningless without further analysis. It's a very dangerous business to just look at a data set and derive a pattern with your own eyes and go, well, it's quite obvious this is the case. You know, look, these trout are much longer than the salmon. But that is something we want to avoid, because that's when you produce spurious or casual correlations or patterns. We want to analyze it emotionlessly so that we get true patterns and tell the true story. Okay, so as I discussed probably ad nauseum in that previous slide, we're looking at numerical data now, and we're going to begin our journey through describing that data or summarizing that data. What methods do we use to summarize large data sets? If you pause this audio now and go to the data set available to you as an Excel spreadsheet called Melbourne Cup Winners. If you go there now, download that, have a quick look at it, you see this is a classic data set. What you have there presented in two columns are the first 20 Melbourne Cup winners from 1861
I believe it is, through to 1890, around that mark. And then the most recent 20 Melbourne Cup winners. And for each of those horses, we've got a numerical piece of data, being the age of the horse when it won and the time it took that horse to win that race. So we've got 40 data points there. This is a classic data set, a classic numerical data set. And look, in that far left-hand column with the years, we have a categorical data. So we're pigeonholing these Melbourne Cup winners into the particular year they're in, and we have attributed some numerical data to each of those categorical variables. So we have two data sets within this, or two subsets within this larger data set. We have the earliest winners, the first 20 years, and we have the most recent winners, the last 20 years. How do we summarize these two data sets so that we can quickly compare them? Quickly look at two numbers and go, all right, I can compare these side by side. Well, the primary one we use, which I'm sure you'll be familiar with, is the mean, also known as the average. And the mean is simply the typical value, or the center of the data set. And we call it the center because later on we'll be looking at the distributions of data on a horizontal plane, and the mean makes up the center of that distribution. But we'll get to that later. For now, we just need to remember that the mean is the average, and the average is the typical value. And we get that typical value by adding up all the data in a data set that we're analyzing and divide by the number of data points. This is provided to us here in mathematical formulae, where each individual data points is given the letter X with a subscript for the number as where it falls in the data set. So X1 is the first number in that data set. X2 is the second number in that data set, so on and so forth, and Xn is the final number in that data set. So if we're looking at the first 20 winners of the Melbourne Cup, the last data point would be X subscript 20, the 20th piece of data. So we add these together and we divide by the sample size, which is 20. So that in the middle of the formula there, we have that given quite simply, x1 plus x2 plus ... all the way through to xn. So there'd be plus x3 plus x4 plus x5 through to x20. We add all those up together, divide by the sample size, and that gives us the sample mean given the nomenclature x with a bar on top. So x bar. See that on the left hand side, so x bar equals that formula. Shorthand for that long formula is using the sum symbol here, as sort of a large stylized E. So when we have this large stylized E, the sum symbol, what you do is you sum all the data points to the right of that sum symbol, this large E. In this case it says sum all the data points X, and it's got a subscript I, and when it's got subscript I, the I means all the data points. So in this case, X, or sum, E, the large E, sum all these data points, X1 through to X20, and we've got 1 on N, so we sum them all and divide by N. So it's just a shorthand way of this of showing this larger formula, and we'll see this sum symbol quite often. So X with a bar on top is the same as adding all the data points together and dividing by the sample size, and in shorthand this is 1 divided by N times the sum of all the data points. So that would give us the mean for the first 20 winners of the Melbourne Cup, and then we do the same thing for the final 20 winners of the Melbourne Cup, and all of a sudden we'd have the average age of the horses in the early years and the average age of the horses in the most recent years. We can do the same for the time it took, and we're given the time in seconds, so we can get the average speed that it took to win the race in those particular years. When we're taking the average of a sample set of data, so remember, a sample is a subset of a whole population we use to get a representation of the whole population. That's when we use the nomenclature X with a bar on top to represent the mean. If we've got the mean of the entire population, so if we got the age of every single runner in the Melbourne Cup ever, that would be the entire possible population, we give it this funny U symbol here, mu. So it's careful to remember this. When we're showing the mean of a sample, we use this X with a bar on top. When we're using the mean of a population, we use this funny mu symbol, which looks like a U. Alright, so we've seen the mathematical formula for the mean, also known as the average, which gives us the centre of the distribution, or the typical value of a data set. If you've got a large data set, obviously summing all those values together by hand and dividing by the sample size is a laborious process. Thankfully, we have software packages to do this. With a calculator, it obviously makes things simpler, but with Microsoft Excel, it's even easier than that. The function within Microsoft Excel for doing the mean is equals average bracket, and then you put in the cells which you want to average. So when you have this formula, the equals at the front is telling Excel that you have an equation to do. The average says, alright, I want you to do an average for me and average anything which comes in brackets after that word. So any data points you put in those brackets will be averaged, or you'll get the mean of. Here I've got A1 colon A2, which means it will average every data point between A1 and A20 in the first column. If you look at the video for Melbourne Cup winners, you'll see me talking through that formula and how it works and how it can be done very quickly. Using Minitab, go to the Stat menu, select Basic Statistics, then Descriptive Statistics, click on the column of data that you wish to calculate the mean of. It says median there, it should say mean. Click the statistics within that box and check the median box. Watch the video on Minitab for the average, which is available on Moodle. So as a practice, please get that Melbourne Cup winners data set off Moodle as described in the datasets folder at the bottom of the Moodle page, and calculate the average age and winning time of the first and most recent 20 winners of the Melbourne Cup with that data provided to you. Again, there's a video to demonstrate how to do this, but it is fairly simple. As we go through, we'll have plenty of these practice data sets for you to practice these mathematical functions in these software packages. Also see there's a Minitab version of the same thing for you to practice as well. So after you've calculated those averages or means for those two variables, being winning time and age, you'll see that the values are different, and it would be an extremely huge coincidence if they weren't different. But the question is, are they different just due to chance, or are they different for a reason, which we refer to as significantly different? And when we get into inferential statistics, we'll look at methods to work out whether or not the first 20 Melbourne Cup winners and the most recent 20 Cup winners are different, not due to chance, but for a reason. So we've looked at the average, and that's pretty easy. We just sum all the values and divide by the sample size, and we'll be doing that a lot, as I said, in statistics, because a majority of statistics is really just comparing means. However, it's not always appropriate to use the mean to find the centre of a data distribution or to find the typical value. And this is when our data sets are skewed, that there might be more smaller values than higher values, or there may be a few really extreme high values and lots of small values. And a classic example of this is in real estate house prices. Often in suburbs you get a lot of houses which are sold at around the same price, and then you might get some really expensive ones at the top of the scale which may have more real estate, more land, or they may be on a particular good street. And if you're going just on the mean, that may actually change the mean substantially when it doesn't really represent the typical value in that suburb. What I've provided for you is another data set called House Price Shelbyville, about an imaginary town called Shelbyville, with a list of recent house sales and the price that those houses were sold for. That data set's available to you in Excel, and what I've got here is a histogram, and we'll be learning how to make histograms in the next topic. But what it's showing, very simply, is bands of house prices. So on the x-axis of this graph, in the left hand most unit, we have houses which were sold between $250,000 and $300,000, and you'll see that there's no bar there, so there was no houses sold for that price. The next unit across, we have $300,000 to $350,000, and we'll see that there is a bar there, so some houses were sold for that value. And on the y-axis it shows us the number of houses that were sold in that price bracket, and we can see that between $300,000 and $350,000 there was 4 sold in that bracket. Between $350,000 and $400,000 there was 5 sold, and between $400,000 and $450,000 there were 2 sold. And then there's just no houses sold between $450,000 and $750,000, and then we get up to the $750,000 to $800,000 bracket, and there's 1 house sold, and then $850,000 to $900,000 there's 1 house sold. So we've got a very skewed data set, skewed to the left. So let's examine a way that we can come up with a measurement for the center of this we can use to summarize the data set. So the way we do this is not using the mean, but a value called the median, M-E-D-I-A-N. And the median isn't found by adding up all the data points and dividing by the number of data points. It is actually the midpoint of the data set, so the actual middle value. So if we lined up all the values in the data set from the lowest to the highest, it's the middle value from 1. So if there's 21 numbers, we rank them between the lowest and the highest, first being the lowest, the 21st being the highest, and the middle number in that case is the 11th number. So we can find what this middle number is very simply. If there's an odd number of values, to find what the middle value is, we just get the sample size, add 1 to it, and divide by 2. So if there's an odd number of values, we find the middle value by getting the sample size, adding 1 and dividing by 2. So if there's 11 data points, we'd go 11 plus 1 is 12, divided by 2 is 6. So we look for the 6th number in the line from the lowest to the highest. The example we have here is a data set containing 9 values. 9 is odd, so we'd use the formula n plus 1 divided by 2. So we'd go 9 plus 1 is 10, divided by 2 is 5. So we want to look for the 5th value in the row of numbers from lowest to highest. So I've arranged this example data set from lowest to highest, and we count along. 1, 4, 7, 7, and then the 5th number is 8. So the median in this data set is 8. If the data set has an even number of data points, it's a little bit more complicated, but not really. We use the same formula. However, in this case, we average the data from either side of this number we get from the formula. So, to explain that better, if we have 10 numbers in a data set, we plug 10 into that formula, so 10 plus 1 equals 11 divided by 2 is 5.5. Obviously, there's no 5.5 number in this line from lowest to highest, so instead we find out what the fifth number and the sixth number is, because the fifth is before 5.5 and 6 is after 5.5. So we count along this row, find the fifth one, it's 8, 1, 4, 7, 7, so the fifth one is 8, then the sixth one is 9. So we simply get the average of 8 and 9 by adding them up and divide by the sample size, which is 2, so 8 plus 9 divided by 2 is 8.5. So the median of this data set is 8.5. So there's no actual formula for calculating the median like there is for the mean. It can only be done by counting through from lowest number to highest number. But fortunately, these statistics programs do the hard work for us. So if you had 200 numbers, it would take a long time to order them from lowest to highest and then count up. So Microsoft Excel has a formula for this. It's simply equals median brackets the data set close bracket. So in this case, I've gone A1 colon A20, and within that formula, Microsoft Excel would find the median of the values found between A1 and A20. Using Minitab, it's very similar to finding the mean. We go to the Stat menu, Basic Statistics, select Descriptive Statistics, click on the column you wish to calculate the median for, click Statistics, and then check the median box, and then OK. So download the House Prices Shelbyville file, which has the data from recent house prices in Shelbyville, and calculate the median and the mean for this data set using the formula we've just learned, and compare what you've got, the mean and the median, to the histogram, so the distribution of house prices, and just from your observation of the small data set, and ask yourself, what do you think is the best representation of the average house price, inverted commas, average house price, or most typical house price in that area? Which one do you think would give you the best indication of what house prices are like in this area? When we move on from here now, we'll be looking at how we measure the spread in the data, and in the next topic, as I said before, we'll be learning the ways to produce these histograms and other ways to show whether or not data is skewed and how it's distributed. So we've looked at two ways now to show or summarize the center of a data set, the typical value. Now we want to look at the way that we can describe the spread of the data. What is the range of our data set? And it's important we have a method for that, because if you look at these two small data sets provided, and if you calculate the mean and the median of both of them, you'll find that the mean and the median is the same for both dataset 1 and dataset 2. But you look at dataset 2, the range of it is only from 4 to 6. It's a very tight data set, very consistent values. Whereas if you look at dataset 1, it ranges from 1 to 11, and the data points are all over the place. We need a way to show that dataset 1 is different to dataset 2 without just relying on the mean and the median. And for this, we'll use the standard deviation. Deviation is a concept that has struck fear into the heart of students and scientists for a very, very long time. However, it's extremely simple. What the standard deviation gives us is a measure of the variation around the average or the mean. So if we have a mean figure, how representative is that mean of the entire data set? So if the standard deviation is large, that means that we have a mean, but there's a lot of variation around the mean. There's a lot of data points which don't resemble the mean value at all. If the standard deviation is low, it means that the mean is very typical of most data points in the set. Technically speaking, the standard deviation is the average difference between the mean and each data point. And we'll see this as a mathematical formula on the next one, but it's calculated very simply. You calculate the mean of a data set and then subtract the mean from each data point, square that difference, and then add them together. Then divide by the sample size, put simply. Again, there's a difference in the nomenclature for the standard deviation between the standard deviation of a sample, remember, which is a subset of a population, and the nomenclature used for the standard deviation of a population. And here they are given on this slide. It's important that you remember that the standard deviations for a sample and a population are represented differently, because we'll be using them in slightly different fashion down the track. Now, the halfway point to calculating the standard deviation is calculating a term called the variation. And I put this one in first because it's a slightly simpler equation and it is used in certain facets of statistics, the variation rather than the standard deviation. But the variation is very simple. It is as I described in the previous slide. You get each data point in the data set, subtract the mean from it, and square that difference. So here we have it represented at the top of this fraction. So x1 minus the mean, we know that's the mean, in brackets, so we do that difference and then square that value. Then we add that to x2 minus the mean squared all the way through, and we divide by n minus 1. And we'll have a look at why you divide by n minus 1 a bit later on, but for now we can just see that we divide by n minus 1, and that's what we need to know. The shorthand for that again is using that sum symbol, sum all the differences of a data point minus the mean squared divided by n minus 1. To get to the standard deviation from this variance, it could not be easier. We simply take the square root of this entire formula. So the variance is the sum of the difference between the mean and each data point squared divided by n minus 1, and the standard deviation is simply the square root of the variance. So the standard deviation is the square root of the variance, which is the square root of this entire formula. Easy. So two things we need to understand for the standard deviation before we go into an example. There's two things which helps explain that formula, which on the outset looks a little bit ugly, but it's not really that ugly when you break it down. It's just simply the difference between the mean and each data point squared. We square each difference, so the data points minus the mean squared. We square all these differences to make them all positive, because with a mean, some data points will be lower than the mean, some will be larger. If a data point is lower than the mean, that means if you subtract the mean from it, it will be negative. So we want them all to be positive, so we just square them. By square rooting them after that, that brings them all back to the original number, but they have all the same magnitude. So this is a way to make the standard deviation only positive. Also, if there were some positive figures and some negative figures, they'd all cancel each other out, and we get a standard deviation of 0, which is not what we want. We divide by the sample size minus 1 because we actually divide by something called the degrees of freedom. Now, degrees of freedom can be a confusing concept, and it's not generally one that I explain very well, but there's many explanations for it out there, but it's a simple concept. We divide by n minus 1 because the sum of each data point and the mean is always going to add to 0, and we'll see an example of this. Therefore, the sample size minus 1, if there's 20 data points, only 19 of them can actually vary, because the last one must always make it sum to 0. Therefore, only the sample size minus 1 of these deviations, a deviation being the mean minus, a data point minus the mean, can actually vary freely. So the degrees of freedom is the sample size minus 1. Let's look at this concept with an example. We have a very small data set here containing 1, 1, 2, 2, 3, 3. So it's a six data points in this data set. So n equals 6. The mean of this data set is 2. So the average of this data set is 2. So we can calculate the sum of all the deviations, which should equal 0. Right? And each deviation, remember, is a data point minus the mean. And so we calculate each of the deviations. So that's each of the data points minus the mean, and then sum together. So we have the first data point is 1. So the first deviation is 1 minus 2. The next one is 1 again, so that's 1 minus 2. 2 minus 2, then 2 minus 2, 3 minus 2, plus 3 minus 2. Sum all those together, so the sum of the deviations, each of these 6 deviations, and we get 0. Right. Therefore, so we've got 1 minus 2, 1 minus 2, 2 minus 2, 2 minus 2, 3 minus 2. That gets us to -1. If you sum those first 5 together, we get to -1. But we know the sum of the deviations has to equal 0. Therefore, this last deviation, 3 minus 2, must always equal 1. It can't equal anything else if the sum of the deviations is to be 0. Therefore, only 5 of these deviations actually vary freely. They're the only ones which are free to be whatever they want. So we've seen how summing the individual deviations gets us 0. So now let's expand this data set out and calculate the standard deviation, or the average deviation, using the full standard deviation formula, which is that variance formula, the square root of that variance formula. So each deviation, individual deviation squared to make them positive, divide by the degrees of freedom, which is the sample size minus 1, and then the square root of that. So we have 1 plus 1, well, -1 squared is 1, -1 squared is 1, 0 squared is 0, 0 squared plus is 0, 3 minus 2 is 1 squared is 1, 3 minus 2 squared is 1. So we have 1 plus 0, 1 plus 1 plus 0 plus 0 plus 1 plus 1, which is 4 on 5, which is 0.8, and there I've managed to put in a fantastic error, so it should be the square root of 0.8 is the standard deviation. See, we're all fallible when it comes to stats. So it's 1 plus 1 plus 0 plus 0 plus 1 plus 1, which is 4, so 4 divided by 5, which is 0.8, and the square root of 0.8 is the standard deviation. The variance is 0.8. The standard deviation, which is the square root of the variance, is the square root of 0.8. We show, even though I've incorrectly put here the standard deviation of 0.8, we represent the standard deviation next to the mean in brackets in things like journal articles. So the correct nomenclature for the mean and standard deviation in this case would be 2 bracket 0.8 bracket. Well, not 0.8, but the true standard deviation, which is the square root of -0.8. So how do we use Microsoft Excel and Minitab to calculate the standard deviation? Well, it's very simple, and it's very close to the median, and so close to how we calculate the median that I've copied and pasted it in and not changed some of the wording on this slide, which is fantastic. So using Microsoft Excel to get the standard deviation, we just use the formula equals STDEV bracket the cells that we want to get the standard deviation of, close bracket. In Minitab we use a very similar method that we'd use for the mean and the median. Stat menu, click basic statistics, then select descriptive statistics, click on the column you want to calculate the standard deviation for, click statistics and check the standard deviation box. Here's a chance to practice using the standard deviation. Go back to that data set, house prices, Shelbyville. and use the equals STDEV formula to calculate the standard deviation of house prices in Shelbyville. Now play around with this standard deviation. Try deleting one of the more expensive houses and see how that changes the standard deviation. You'll probably find that standard deviation drops because one of these extreme values is removed. Now put that value back and delete one of the more typical values in the $300,000 realm. You'll see that the standard deviation doesn't change as much. This shows that extreme values have a large effect on the standard deviation, and we'll find in later topics that the larger the standard deviation is, the harder time we have in being confident in our conclusions from statistical analyses. Now, before the next tutorial, find a study based on your area of interest. It might be in viticulture, it might be in equine, it might be in agronomy, it might be in aquaculture. Find a study that presents the mean and standard deviation of a particular variable in this field, and have a look at how the authors used this information and what conclusions they drew from these descriptive statistics. And then we'll each present this very casually in the next tutorial. So not only will we see how the mean and standard deviation have been used, but we'll also learn something about our particular field.